I hope you like the inverse CDF method. It works like magic when it works. However, it has its own limitations. For many situations, for example, when it is difficult to find the analytic expression of the inverse CDF, or when the inverse does not uniquely exist, for example, for multivariate distributions, the inverse CDF method is simply not applicable. In these cases, we will not be able to implement the inverse CDF method to draw random samples. Under these scenarios, an alternative solution is using the acceptance rejection method. Using the acceptance rejection method requires us to specify something called a proposal distribution. Suppose that we want to draw x, a random variable x, with probability density small f and support R, which is a subset of the real numbers. We're considering the case of univariate X over here. However, you should know that this procedure should be generalizable to multivariate distributions as well. In that case, we replace the real numbers by Rn, where n is the dimension of the random variables. Implementing the acceptance rejection sampling requires us to first find a proposal distribution, that is, another random variable y with density g, so PDF g, that satisfy the following inequality. Ft divided by gt is less than or equal to a constant c for all possible t values, and for some constant c between 0 and infinity. So what exactly does this inequality mean? It tells us that ft over gt is bounded. In other words, it can't be infinity. It has to be less than or equal to some fixed constant c, which is less than infinity. Further, we know that whenever ft is greater than 0, gt also has to be greater than 0, because we don't want the denominator to be equal to 0 when ft is not equal to 0. In other words, the support of y, the proposal distribution, should contain the support of x. To draw random samples x's from the PDF f, in other words, I would denote this by x follows the PDF f over here. If we want to draw the sample using acceptance rejection sampling, then we can implement the following 4 steps. Step 1 is finding a proposal distribution y that is easier to sample from. So instead of sampling from x, subsequently we'll be sampling from y. So we want to find a y that we can directly or easily sample from. And the PDF of y, g, needs to satisfy the earlier inequality, where ft versus gt divided by gt is less than or equal to c for some constant c that's less than infinity. So in addition to the proposal distribution, we also need to find or give a c value. One more note. So over here, we can set c to be any constant that makes this inequality satisfied. However, we will see later that the smaller the c value, so the closer it is to 1, the better it will be. So step 1, we have specified a proposal distribution y. Step 2 will be drawing y's from its own distribution. So we want to draw a random sample of y, which has the PDF of g. In step 3, we draw another random variable, a uniform random variable between 0 and 1. And in step 4, we implement the acceptance or the rejection. Specifically, we do the following. If the u we drew in step 3 is less than fy divided by c times g of y, where y is what we drew in step 2, then we're going to accept y. And by that, we mean that we're going to set x equal to y. So y is going to be a good sample of x. Otherwise, so when this inequality is not satisfied, we want to reject y and repeat steps 2 to 4, obtain a new sample, and we iterate this until we have obtained an accepted sample of y. So under this acceptance rejection procedure, it is possible for us to calculate the theoretical probability of acceptance. So what is the probability that we sample a y and this turns out to be accepted as a valid sample of x? The probability of acceptance is equal to the integral from negative infinity to infinity, the probability of acceptance given a particular y times gy dy. In other words, in this step, we're integrating out the random variable y by considering all its possible values and its density. And this is equal to the integral from negative infinity to infinity of probability that the uniform random variable u is less than this ratio over here times everything afterwards. So we can see that we're replacing the probability of acceptance given y by the probability that the random uniform variable u is less than this ratio. And this is equal to the integration from negative infinity to infinity of what is inside the parentheses over here. So fy divided by cgy times gy dy. And this step uses the fact that for the uniform random variable between 0 and 1, the CDF is equal to this thing itself. So fu of t is equal to t for any t between 0 and 1. Now you can see that inside the integral, we have gy on the denominator and gy over here. So we can cancel these out. And we can also pull out the constant of 1 over c. So this becomes 1 over c integral from negative infinity to infinity of fy dy. And we know that this should integrate to 1 because fy is a PDF and all PDFs should integrate to 1. So this thing is equal to 1 over c. In other words, when we implement the acceptance rejection procedures, the probability of an acceptance is going to be equal to 1 over c. This tells us that the closer c is to 1, the larger 1 over c is going to be. Then the more likely for the samples, or the y's, to be accepted. The larger the c value, say if c is 100, then 1 over c is about 0.01. This will mean that out of all of the y's that we draw, only about 1% of them will be accepted as samples of x, and the other 99% will be tossed away. And that's a lot of computational power that's wasted over here. So what this says to us is that intuitively, we want c to be as close to 1 as possible. So we want to find a good proposal distribution and a good c value so that the earlier inequality is satisfied. Then when the c is low, we're going to have higher chances of acceptance, which means that we can draw the samples with lower computational burden. Intuitively, the ratio ft divided by gt would be close to 1 when the two distributions, the original distribution and the proposal distribution, are quite similar. In other words, for every t value, every possible t value, f and g are approximately equal.